we're gonna review Chapter 9, covalent bonding in orbitals, which has a little bit of the valence bond theory in it, and the rest of it is molecular orbital theory. So what I want to do is share the review document. Oops, went about that the wrong way. Here we go. Share this one. There we go. And we'll work from this. I assume, yeah, that's the review. Okay. Now, I didn't have time to pick out the questions beforehand, so I'm going to have to sort of wing it. And I'll just mark them off as we go so I don't backtrack. Well, let's start with this first one. And it speaks to the issue of orbital hybridization. Remember, hybridization was a fix that was proposed by Linus Pauling to account for the symmetry of some, or the geometry of some molecules where the atomic orbital overlaps couldn't explain it. And our example was methane, because carbon has 2 s orbitals and 2 p orbitals, 2 electrons in the s orbital and 2 in the p orbitals. And if you simply overlapped orbitals, you would not get a tetrahedron. So let's look at these possibilities. I'm not going to draw them up here. We'll just put one up there for reference. All right, which of the following molecules contains a central atom with Sp2 hybridization? Well, maybe I better. So for this one, we have aluminum and phosphorus tied together. And then we have chlorines here, chlorine there, and hydrogens here. Okay, so what do we know about Sp2 hybridization? We know that it results from 3 electron groups in a bond or in lone pairs. So if we look at this one, we find that, well, I didn't draw in the, like that. If we look at the central atoms, here we've got 4 groups. So that type of hybridization is Sp3. This one is also 1, 2, 3, 4. That's Sp3. What about this one? Well, this one doesn't need any hybridization because it's only overlapping. It's only bonding on one side. Although it could be. Yeah, in fact, it is. And I correct myself. These are also Sp3 hybridized because they're 1, 2, 3, 4 groups. So you need only one of them to form the bond, and the other 3 house the lone pairs. So this one doesn't answer it. That's not Sp2 hybridization. How about this one? Where we have fluorine, like that. The central atom has 3 groups and no lone pairs. So that would be Sp2 hybridization. It has 3 equally distributed hybridized orbitals so that they can overlap in a trigonal planar format, like this. So B fits. And if you're in a hurry in a test and you find that as the right answer, and there's nothing else down here that says 1 of the above, 2 of the above, none of the above, and all that garbage, then you know you hit gold and you can move on. B is the answer. If we just look at these others, there are 1 for this one. Let's see, I don't know if I can highlight it. Yeah, let's see, highlight there. This one has 1, 2, 3, 4. Sp3 hybridization. How about this one? You got 1, 2, 3 plus the lone pair on each nitrogen. So that's also Sp3 hybridization. Okay, how about this one? This one only has 2 around beryllium. And notice that that means that beryllium does not have an octet. But it still requires, since it's only got 2 groups, and the geometry must be linear. Linear means Sp hybridization. So that last one, E, beryllium dichloride, is Sp hybridization. The only one that fits that definition that we want is B. All right. So let me mark that one off so I don't do it again. Come back and look at it again. Let's see. I'm going to jump around probably. How about let's go down to number 3. And this, you'll notice that this review document is version 2. There's also a version 1. I used to have, I may have said this before, but I used to have everything drawn together into one version. And there were like 130, 140 different problems. That was just too much. So I went through them and I found duplicates, concepts, and separated them into separate documents. So if you go through one of these, then you should have covered all the topics that would be necessary to do well on the exam. Okay, number 3. What about this molecule? What do we got here? Well, let's see. We've got 4 carbons. And we've got a nitrogen on the end. We've got a chlorine here. And that's a hydrogen. And 1, 2, 3, 4. 1, 2, 3, 4. And it's supposed to be 4 carbons. 1, 2, 3, 4. There. Oh. My mistake. I should have known better. Carbon's only good for 4 bonds anyway. Now, and these are all hydrogens, I believe. There we go. Okay, so what's the question here? What is the hybridization of the carbon atom that is double bonded to oxygen? Well, the temptation is to say, well, there are only 3 bonding groups here, 3, so that's trigonal planar, right? Sp2 hybridization. And you might be right, but you also need to watch out for lone pairs, just to be sure that there are no lone pairs. And the best way to do that is to look for octets. So you have 2, 4, 6, 8. Carbon's got an octet, so it's complete. This one's got an octet. That one's got an octet. Nitrogen doesn't have an octet. So if you look at how many valence electrons it has 1 there, 1 there, and 1 there. Remember, we talked about formal charge, I think. So half of those go over here. 1, 2, 3. And nitrogen normally has 5. So it needs these other 2 right there. So that gives 2, 4, 6, 8 octet. Now we're good. Everybody has an octet. But the question was about this carbon right here. That carbon is Sp2 hybridized. This one is Sp3. 1, 2, 3, 4. That one's Sp3. This one, this carbon is P. It's only got two groups, there and there. How about nitrogen? Nitrogen is also sp because it's got a group here and a lone pair there. Now that wasn't the question, but I figured while we're here, we might as well look at each one of them. And if we were to do 4, I think I just answered 4 and 5. 4. The nitrogen atom would be sp hybridized. Okay, so we did both of those. How about, let's see, hold on a second. Let me flip the page here. I might skip around a little bit. Oh, here we go. How about number 6? Go down to number 6. Here we go. All right. So what's the hybridization here on the selenium atom in SEF6? So where's selenium come from? Selenium's from the 4th period, right? So it has access to d orbitals. That ought to be a clue right there. So I have SEF6. So 6 times 7 is 42, correct? Electrons. And selenium is in the same group as oxygen, so it has 6 electrons. So that means 48 total electrons. So we have selenium, 2, 3, 4, 5, 6 fluorines. Okay? And that's 2, 4, 6, 8, 10, 12, which would be 36. So if we do like this, around each one of them, that's 6 extra ones. 6 times 6 is 36. We've all used up. Just use your imagination. Put electrons around all those fluorines. So how about selenium? It has 1, 2, 3, 4, 5, 6 groups. Which is what? Octahedron. Right? And if you need 6 hybridized orbitals that are equally spaced, and that's how they have to be to make an octahedron, if they're equally spaced, then you need 6 orbitals. Well, you can get 4 of them out of sp, right? Right? But you need 2 more. Fortunately, selenium is in the 4th period. It has access to d orbitals, so you have 2 ds. So D2sp3 would be the hybridization for selenium here. Let's see. Here it is, D2sp3. All right. Let's see. I might have to go back. Well, I may have to backtrack, but that's okay. What about well, while we're here, let's do number 8. Position that. 8 can give you trouble simply because it's got so many bonds in there, so many atoms. If you're familiar with the name tetracyanoethylene, you could figure it out really quick. But that's organic chemistry, and we haven't got there yet. So let's try to draw the Lewis structure for this whatever. it's given you the starting structure, right? Because if it just gave you the molecular formula, it'd be kind of hard to tell what goes where. So we start off with this structure, that's given. And then we just need to fill in and put all the electrons where they need to be, right? So how many carbons do we have? Well, let me draw it. We got that one, and then we have carbon here, carbon here, carbon here, carbon here, right? And then we have nitrogens here. There we go. Now we have 1, 2, 3, 4, 5, 6 carbons, which is 24 electrons, right? And we have 1, 2, 3, 4. Yeah, 4 nitrogens, which is 4 times 5 is 20. So we have 44 electrons. And the rule is you start from the outside and work your way in, correct? So let's fill this one out here, 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 and here. That's 6 on these 4. Oops, too many. All right, so we have 4 times 6 is 24. Well, we haven't subtracted the bonds yet, have we? So let's do those two. 2, 4, 6, 8, 10, 12, 14, 16, 18. All right? So that would be, let's see, 30, 42. That'd be 2 electrons left over. So where do those 2 electrons go? Well, if we follow the rules, we'd have to put them on maybe one on one and one on the other, or both of them on one of these carbons. But look what we got here. Okay, follow me for a second. If we need to make an octet out of this carbon, it's easy. You just take these electrons and make some bonds here, and that carbon's taken care of. Same for each one of these on the outside. So if we put 2 electrons here, then that kind of spoils that party. But if we put those 2 electrons here, then we've got 2, 4, 6 here, 2, 4, 6 there. And then we've got those 2 electrons that can make a double bond here and give this one an octet, that one an octet. And these octets can be made from the nitrogens. That's why I wanted to do this one, because it's not straightforward. If we just follow the rules, then we put the electrons on the wrong carbon. But if we put those 2 extra electrons, say on that side, now we can make our octets like this, right? We just take 2 pairs from here, like that, take these 2 pairs, like that, like that. There we go. And then we take these 2 pairs and make a bond there. Now everybody's got an octet. Okay, so now that we have our Lewis dot structure, we can decide and answer the question, how many atoms are sp hybridized? Sp means only 2, right? Only 2 groups. So how many atoms are sp hybridized? Well, these carbons are obvious, right? 1 group there, 1 group there, 1 there, 1 there, 1 there, 1 there, 1 there. So that's 4. But notice the nitrogens. The nitrogens have a group on this side and a lone pair on that side. So they also have to be sp hybridized. Right? Got those. What about this one? That's sp2 hybridized. 1, 2, 3. 1, 2, 3 for that one. So 8 of these atoms are sp hybridized. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 2 of them are sp2 hybridized. So that's why the answer is 8. The temptation, if you get this far, the temptation is to only look at the carbon because it's got a bond here and a bond here. But that nitrogen has to be hybridized for this side and for the lone pair. So that's why the answer for this one is 8, not 4. All right. Let's see. Let me mark that one off. Okay. Let's go on to 9 now. I think 9 has something to offer. Actually, well, I'll put this up here for clarity. A pi bond is the result of what? Okay, let's find out which one of these is the true statement. Overlap of 2 s orbitals. No, can't be. Overlap of 2 s orbitals always gives you a sigma bond. The overlap of an s orbital and a p orbital will also give you a sigma bond. Overlap of 2 p orbitals along their axis. That means you got an element here and an element here, and you got this one, and you got this one. That's on axis. That's a sigma bond. It's not a pi bond. Sigma bonds are all on axis between the atoms. Pi bonds are always off axis. So we've already determined A, B, and C are wrong. How about D? Sideways overlap of 2 parallel p orbitals. That's true. And then we can go to E, sideways overlap. S orbitals don't sideways overlap. Right? S orbitals are spherical. Right? So they just come together and they overlap. More or less like this would be a sigma bond for overlap of 2 s orbitals. Or similarly, you could have something like that, not exactly like that, overlap of p orbitals. Or a p and an s would also do that. But the sideways overlap of 2 p orbitals, you've already got your sigma bond here. Then you have like that, then you get some overlap here. And that's your pi bond. Now the reason we draw it like this is so we can see the other stuff in there. But these p orbitals are not really like that, like those figure 8s. They're really, they balloon out a lot more, so there's more overlap there than you would suspect. It's not as strong as a sigma bond, the pi bond, but it does add strength to the total. All right, so that makes D the answer here. Okay, let's mark that one off and see what's next. How about, let's see. If we go down to 10 and 11 are using the same figures. I wonder if they are related. Probably are. So we'll do 10 and 11 together. We'll do 10 first. Okay. We're going to use these structures to answer the question. Now, one thing about these, this is organic chemistry again, and these 3 structures are ring structures. And at each intersection of a line is a carbon atom. Right? So each one of those is a carbon atom. We just don't write them in. And then this represents the double bond, double bond, double bond. There's your single bonds. Okay? Also, what we don't write, unless we absolutely have to, is hydrogens. So this would have a hydrogen here, 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 there, there, and there. That's benzene. C6H8 is similar to that one, Only now it's missing one of those double bonds, right? So it only has one here and one there. I think that's the way they're written. Yeah. But you still have hydrogens. Now, wherever you have 3 bonds, 1, 2, 3, you only have 1 hydrogen. But where you only have 2 bonds, you've got 2 hydrogens. And you can see that from the formula. Notice when we took that double bond out, that gave us 2 hydrogens extra. We had 1 there and 1 there. We got 1 there and 1 there now. Okay. Similarly, for this one, now we've only got 1 double bond here. Right? So this one will have a hydrogen, and that one will have a hydrogen, and this one will have 2 hydrogens, 2 and 2. Right. So now we just add 2 more hydrogens. Instead of H8, it's H10. Okay. So I just wanted to explain how these things are written. So let's answer the question. Which molecules have p orbitals that share an electron pair to create pi bonding? Right. How do you know the pi bonds? How do you know pi bonds? If you've got a double or a triple bond, there are pi bonds there. Single bonds are always sigmas. So these right here would be considered sigma, sigma, and sigma. Well, actually, they're all sigmas around here. But this one also has a pi, that one has a pi, and that one has a pi. Anywhere you have those double bonds, you have pi. So all of them have pi bonds. Right? You just look for the double bonds or triple bonds, whichever the case may be. Triple bonds have 2 pi, like this one. Right? There's a sigma, there's a pi, and there's a pi. Okay. Now while we got these diagrams up here, let's look at number 11. Okay, for the same diagrams, same molecules, which have equivalent carbon-carbon bonds throughout the molecule. All right. Here's something else that needs explaining. Remember at the very end of our discussion where we talked about, not resonance. Shoot, my mind's gone blank again. I'll tell you what. Just a second. Delocalized. The word I'm looking for is delocalized. The electron density picture would give you delocalized smearing of electron density wherever you have an intersection of single and double bonds. So you would have some right in this section, not right there. Well, not right there either. How about like that? Right in there, and you would have some right in here. But for this one, you've got alternating double and single bonds all the way around that molecule. So you've got smearing, delocalization of electron density around that entire molecule. What that does, well, let's start with this one, with just the one double bond. This is a single bond. It's going to be a certain bond strength and a certain bond distance. Double bonds are shorter and stronger, right? So these bonds are not equivalent around that one. That one's different than the rest of them. These two would be smeared around here. So these three would probably be equivalent, but these would not be equivalent. This one has alternating single and double bonds all the way around. So you have the potential for delocalizing the electron density around that entire molecule. And that means that every bond, every carbon-carbon bond in that molecule is equivalent to every other one in both strength and bond length. That's one of the problems for the localized electron model, because it says this bond should be different than that bond. But it's not. And the localized electron model cannot explain it. Right? That's molecular orbital model has no problem. Now, we measure these bond lengths and bond strengths and find that they are in fact equal all the way around. These have different bond lengths and strengths, as does that one. So the answer to this one is A. The only one that has equivalent carbon-carbon bonds all the way around is benzene. And that leads to another topic in, well, organic chemistry. It's called the aromaticity. Aromatic structures are like that, and it magnifies the strength of the bonding of that ring structure when you have aromatic character. So this molecule, this benzene molecule, would be the most stable, the strongest structure of all those three. Oh, here it is. Okay. I took a course one time in soil microbiology. And we touched on the subject of when a tree falls in the woods, how does it decompose? Right? It decomposes in stages. Right? The first stage is it has to be broken down into smaller chunks. So that's where the wood-boring insects come in, beetles and termites and so forth. And then larger animals come along and they rip it apart. Maybe some bees build a honey nest in there or something. But eventually you get down to small, very small particles. Now the microbes. Well, actually, fungi can work on a tree before it breaks down into that size. So it's instrumental. But what bonds do they break first in those molecules in the tree? They go for the functional groups, the outlying ones. They're easy to attack, and they're weaker. Once they get down to the bonds that are aromatic, like this one right here, and there's some very long chain polymers in trees, for instance, that have these aromatic structures in them. Those have to be attacked last, and they're attacked by very special organisms that have the enzyme systems to break those bonds. Everybody else just leaves them alone because they don't have the power to deal with them. It's just an illustration of how stable these molecules are when they have that aromatic structure. All right, so I've done enough talking about that one. Let's go to number 12. Okay. I think I mentioned, but we really didn't go into it in class, was shorthand notation for molecular orbitals. All right? And this is an example. It's modeled after the electronic structure shorthand that we used for individual atoms. Right? You have where we had 1s2, 2s2, 2p6, 3s2, 3p6, and so forth and so on. So here we just put them in order of increasing energy. Left, farthest to the left is the lowest energy molecular orbital. And this sigma 2s was formed from 2s orbitals of either atom. Now this is a diatomic species. It could be homonuclear, it could be heteronuclear, but there are only 2 atoms. Right? We have to keep it simple. My dog hears something outside. There's nothing out there. And if we turn this shorthand 90 degrees, then we could insert it into the energy diagram, right? We could put it like this. And then the lowest one would be the sigma 2s, right? Sigma 2s. And then the next one would be the sigma 2s star, right? Or the sigma star 2s. And the number of electrons in there is the superscript. So we would have, they put parentheses around them. So you have 2 there. So it would be like this and like that. And this would have 2 in it, like that and like that. And then you get to the p orbitals that combine to form molecular orbitals. Now we would have a sigma 2p, right? And it would have 2 electrons in it. And then we get to the pi. The pi is going to have these 2. So that's a pi 2p, and that's a pi 2p. How many electrons does it have? It has 4. 1, 2, 3, 4. Right? And then the last one in this particular molecule is a pi star 2p. It would be up here. So this would be a pi star 2p. And it has how many electrons? It has 2. Like that. Okay. So that's what that shorthand means relative to our energy diagram. Now, all you need to know to answer the question, though, is how to calculate bond order, right? So in this case, we have number 12. In this case, we have how many bonding electrons? Well, we have this one. We have 2. Skip that one. 4, 6, 8, correct? 8 bonding electrons. Minus how many antibonding? Well, let's see. There's 2 antibonding here, and there are 2 there. So minus 4 divided by 2 equals what? 2 is the bond order. Okay? That's why the answer is D. Now, this is a little, the transition from electronic structure in this format to the shorthand is a lot simpler for individual atoms. For molecular orbitals, the chances of having these things flipped with SP mixing is an issue that has to be dealt with. You either have to know the atoms that are involved in the bonds, or you have to just be given it. In this case, you're just given that information, and all you have to know is how to calculate the bond order. So that was the thrust of this particular question. How do you calculate the bond order? All right. Number 12. Keep a close eye on the clock so I don't run out of time. Well, you know me, if I run out of time, it doesn't matter. I'll just keep talking. Let's see, do we need to do that one? Yeah, let's do this one. Number 13. Okay, as the bond order of a bond increases, bond order goes like from 1/2 to 1 to 1.5 to 2.5, 3. As it increases, the bond energy does what? As the bond order increases, the bond energy increases. And what happens to the bond length? Well, as the bond energy increases, right, think of it as a stronger spring, right? So you got the string stretched out here, And if you add more bonds to it, it's pulling, let's see, let me get over here. It's pulling that spring, pulling those atoms together. So the bond strength goes up, bond energy goes up, bond length decreases. So that one answers the question, C. Now, as we've said before, this bond energy increase, just like when we were talking about single, double, triple bonds, the increase is not linear. In other words, if you have a double bond, it's not twice as strong as a single bond, right? Because that second bond, that pi bond, is formed by lateral overlap. They have to, like, there's not a complete overlap. And the same logic you can use with molecular orbitals. But obviously it's a better, a more precise description of the bond strength, the bond order calculations in molecular orbitals. Okay, so let me see, what do I want to do next? How about number 15? Yeah, 15. Okay. So what are we given here? How many unpaired electrons in the F2 2+ ion are based on molecular orbital theory? The order of the molecular orbitals are. All right. So let's say we're talking about this molecule, right? So they strip 2 electrons away to make that ion. So let's look at, it gives you the molecular orbital order here, right here. It doesn't say it doesn't give you the electrons, right? It only gives you the bond, the orbital order of energy. So we would have a sigma 2s, right? We would have a sigma star 2s. We would have a sigma 2p and a pi 2p, right? The difluorine is no sp mixing, right? It's oxygen and fluorine, no sp mixing. Everybody to the left of them, like nitrogen, carbon, boron, on over, those have sp mixing. So we would have the star on this side, and let's see, yeah, and the star on that side. And then we would have this one, right? Yeah. There we go. So we have the sigmas on the outside, the pi's on the middle. So you have, these are lower energy than those two. But this one is a higher energy than that one. Okay, so that's the order. So, how many electrons do we place in there? Do we need to know that to answer the question? The order of the molecular orbitals of this. How many unpaired electrons in this ion based on the molecular orbital theory? Unpaired electrons. So, let's find out how many electrons are required. So, the fluorine is 7 valence electrons each. And notice, we're starting with 2 right here. So that's valence, right? Because fluorine is in the second period. We're leaving out the 1s molecular orbitals. So we only need to consider the valence electrons. So 2 times 7 is 14, minus 2 to make the positive equals 12, right? So we need 12 electrons, right? The first ones are fairly easy, right? You can put 2 here. You can put 2 there. You can put 2 here, right? How many of these do you have? There should be 2 of those right there. So you would have 2, 4, 6. See, we got 6 left over. So we can put 4 in there, right? Like that, that, and that. Okay? So that's 2, 4, 6, 10 from 12 is 2. Minus 4 equals 2. So we have 2 more. So where do they go in this one? Well, this one also has 2 degenerate orbitals, molecular orbitals. Remember what we mean by degenerate. They're the same energy level. They're not perverted. They're the same energy level. So we have 2 here. That means that those 2 go in like that and like that. Okay? So those 2 have to be separated. So to answer the question is, how many unpaired electrons? 2. We have 2 unpaired electrons. All right? That answers the question. Now, what does that mean as far as the molecule goes? Well, if we put those 2 electrons back, they would go here, and the neutral difluoride molecule would be diamagnetic. In other words, it would not respond or be repelled. It would be repelled by a magnetic field. So this one would be diamagnetic. How about that one? It's got 2 unpaired electrons. So this one would be paramagnetic. It would be attracted to a magnetic field because of this unpaired spin. Okay, what else can we say? How about bond order? Right. What's the bond order of, well, let's say if we were doing this one, the bond order of F2. That would be, we would have 4 here, right? Well, let's count up so the 2 extra electrons go into a non-bonding, an anti-bonding orbital. All right? So we didn't even need that one, did we? Right? We didn't need that one. So we have 4, 5, 6, 7, 8. And then the anti-bonding is 2. And the neutral would be 2 plus 4 is 6. Right? So that's a bond order of 1. But if we add those 2 back in there, I mean, if we take 2 away, take 2 away, then we have 8 minus 4 over 2, which would be 2. So what have we done by removing 2 electrons? We've increased the strength and stability of that molecule by taking 2 electrons away. And experimental data, I'm sure, would show that the bond strength for this ion and the bond length would be shorter, the bond strength would be higher than it would for that one. Okay. So I added all that stuff in there. Answer the question is 2 for 15. All right. Let's see. Get me back on track here. There we go. So that was 15. How about, let's see. Well, I'm wasting a lot of time here, aren't I? How about 22? Let's move down to 22. Notice this one has two answers, either A or D. Now, why did I do that? 16, the following statements concern molecules that require resonance, which is true. Pi bonding is most clearly delocalized. For resonance, yeah, that would be required. The benzene molecule is best described by the molecular, well, that's true also. Yeah, A and D both for that one. Okay, well, let's move on. What did I say? 22. 22. Here we go. The hybridization of this molecule. Sort of working backwards, I guess. The hybridization of chlorine in this molecule. So this is 22. And we have ClF2 plus. Okay, so we have 7. 3 times 7 is 21, minus 1, 20 electrons. So we have chlorine, we have fluorine, and we have fluorine. So that's 2, 4 is 16. 2 times 6 is 12. 4. 1, 2, 3, 4. All right. Now we have to well, we have an octet there. 2, 4, 6, 8. So what's the hybridization of, well, wait a minute. Yeah, that's right. It should be Sp3, 1, 2, 3, 4. Right? But I drew that Lewis dot structure wrong, didn't I? It's got to have that plus sign. If you don't have the plus sign in there, then you're going to think that you need 2 more electrons in here. Or you need another electron, excuse me. You need another electron because you've got the positive charge. If you don't have that positive charge, you think, oh, wait a minute, you miscounted. Right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Should be 21 because 1, 2, 3 times 7 is 21. Right, so you got to have that positive there. Otherwise, you drew the structure wrong. All right, that was 22. Let me mark that one off. Oh, here's that molecule again. Think back. We'll just do this one offhand. Remember, we drew triple bonds here, triple there, triple there, triple there. And we drew a double here. So how many sigma and how many pi bonds are in this molecule? Well, the sigma bonds are already there for you. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So it's either C or D. But how many pi bonds? Well, the double bond has 1 pi. The triple bonds have 2 pi's. So you've got 2, 4, 6, 8 plus 1 is 9. So it'd be 9 sigmas and 9 pi's. Okay, let me see here. Yeah, we could do that one if I can find it. Let's see, how much time? All right. I'm going to skip that one and look at how about, oh, we could probably do 26 and 27 pretty quick. I want to get this review document has some tables and short answers in the back, and I definitely want to get to those. What did I say? 26 and 27. Yeah, there we go. So let's do 26. Consider the skeletal structure shown below and draw the Lewis dot structure. Then how many pi bonds does this molecule have? This one should go pretty quick. Nitrogen, carbon, carbon, nitrogen. So we have 2 nitrogens are 5 each, 2 carbons are 4 each. So this is 10 plus 8 is 18 electrons. Right? Yeah. 2, 4, 6. Minus 6 is 12 electrons. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All used up. Okay, now how do we form octets here? Well, the simplest way is to take these 2 here and just put them over there. Take these 2, put them over here. Okay, so that would make triple bonds there, single bonds, triple there, like that. Okay, now the question is, how many pi bonds are there? There's 1, 2, 3, 4. 4 pi bonds in this molecule right there. I'm not sure what that is. I'm tempted to say, but I'm not going to because I'll probably be wrong. So 27 is next. Yeah, 27. Which of the following molecules contains the shortest carbon-carbon bond? All right, in order to be the shortest, it has to be the strongest, which probably means more bonds. So for A, B, C, D, and E says B and D. B and D. B and D are equal. All right, so let's look at them. C2H2, C2H4. This one's probably C2H6, right? And C2Cl4. Okay, these 2 carbons are going to be bound together for every one. All right, except for this one, we're going to have chlorines here. This one, we're going to have hydrogens. 6, excuse me, 6 hydrogens. This one's going to have 4. I don't have room to write the hydrogens, so those are hydrogens. And these are only going to have those 2. Okay? I'll let you in on a little secret. Whenever you see a carbon, carbon's got to have 4 bonds, unless it's an oddball and has some free electrons. But generally speaking, carbon can have 4 bonds, and that's where it prefers to be. So for this one, 4 bonds would be that and that. 1, 2, 3, 4. 1, 2, 3, 4. This one would be 1, 2, 3, 4. 1, 2, 3, 4. This one's already got 4 bonds. This one is 1, 2, 3, 4. So all right, so which one's the strongest carbon-carbon bond? It's that triple bond right there. This molecule is acetylene. This one is ethylene. This one is ethane. This one is tetrachloroethane. No, tetrachloroethene. You just substitute chlorines for each of these hydrogens here. So B and D are similar in strength, but they're not the strongest. Right? The strongest is that triple bond right there. So that's 27. I better mark it off. So backtrack. Okay. All right. Let me see if I can find, here we go. 29. Which of the following species is paramagnetic? So what do we need for paramagnetism? We need unpaired electrons. All right, so 29. Let's see, how many we got? We got carbon, oxygen, fluorine, lithium. Carbon, oxygen, fluorine, and lithium. Homonuclear diatomic elements. All right, so to shorten the workload here, if you look at the back of your review document, and all this stuff will be available for the exam too. We've got on the last pages, right, we've got this diagram like I showed you in the lecture. And here's the order of the molecular orbitals, right? These are no sp mixing. These are sp mixing. The only one that's not in here is lithium. Well, where's lithium? Lithium's on the far left, right? So if you go dinitrogen, dicarbon, diboron, diberyllium, dilithium, they're all sp mixing to the left of oxygen. So you would consider the same series of molecular orbitals for, let's see, these two have the same, and these two have the same. Okay. So actually, you don't have to draw it up here. We can, of course. This one would be, and this is just the valence molecular orbitals, the ones derived from valence orbitals. This would be sigma 2s. This would be sigma star 2s. And this would be pi 2p. Now, is that going to be enough? Right. How many do we have here? We got 8. So that would be 2, 4, and 4 more is 8. Okay, so that one's full. Let's use that same sequence down here. Sigma 2s, because well, actually, sp mixing doesn't matter because you hadn't got to the point where you actually need it, I don't think. Let's see, do you? For dicarbon? Well, yeah, you do. Yeah. Sp mixing is, this one should be replaced by sigma 2p if there were no mixing. 2s and pi 2p. So how many valence electrons of lithium? Well, 2, right? Don't even need those. So what does that say about these? Remember, that one has 2 of these orbitals, right? They're all paired. So this one's diamagnetic, and this one's diamagnetic. So let's look at this one. So instead of that, we're going to have, let's see, sigma 2s, sigma star 2s, sigma 2p, and pi 2p. Then we get pi star 2p. And I think, let's see, 6, 12, 2, 4, 6, 10, 12. Okay, that's all we need. We have 2 of these, 2 of these, 2 of these, 4 here, and 2 here. All right? So these 2 are going into separate orbitals. This is paramagnetic. How about this one? Okay, fluorine should have 14. 2, 4, 6, 10, and then 14. So that's diamagnetic. The only paramagnetic in there is oxygen, right here. Okay? That was 29. Okay, let's see. All right, so I would say that get familiar with this arrangement because it's right there for you, and you can answer several questions just by using this. This tells you that the SP mixing is on that side, the non-SP mixing, no, SP mixing is on this side, no SP mixing on the right. So let's look at, let's see, let me go back. That was 29, what, yeah, 29. Okay, 29. There we go. How about 30? 30 is a good one. All right. For how many of the following diatomic molecules does the bond order decrease if you add an electron? So what would actually decrease the bond order? If you add an electron to an anti-bonding orbital, you will get a decrease in the bond order. All right, so that's what we're looking for. The highest a molecular orbital that has electrons in it or is available to have electrons in it is anti-bonding. If that's the case, then when you add an electron, the bond order will decrease. So let's look at these individuals. We can probably use our table again. So we have this one, diboron, dicarbon, diphosphorus, and difluorine. Okay. So the diboron, the highest orbital is pi 2p with 2 electrons in it. So if you add an electron to that one, you increase the bond order. Carbon. Carbon's highest orbital is 2p, but it's full. So the next one up is sigma 2p. So you add one to that, you increase the bond order. Okay? How about phosphorus? Well, phosphorus is not on here, but it's going to have a similar structure to in its family, the nitrogen. So the dinitrogen, and in order to do this one, we're not in the second period anymore, we're in the third period. So dinitrogen would have the highest orbital for dinitrogen is sigma 3p for phosphorus, and it's full. So what's above that? The pi star 3p. You add one to this, you decrease the bond order. And fluorine, right? The highest fluorine is pi star 2p, and it's full. So we go up to the next one, right? Am I doing this right? How many of the following? Add one electron. Yeah, add one electron. So this is, the next available one is sigma 2p star. Add one there, you decrease the bond order. Let me see. I'm just checking myself here. Yeah. Actually, that answer is wrong. Look at there. This one says that only one of them would increase the bond order. We just proved that the bond order would be, would be increased for two of them, right? Wait a minute, was it increased or decreased? Decreased. So it would be decreased for two and increased for the other two. All right. Let me save that. There we go. All right, found a mistake. I better mark that one. Number 30, and fix that. This should be C. There we go. All right. So that was 30. How about, I'm trying to maximize our impact here. How about 39? Oop, another page. There we go. 39. Okay. In the molecular orbital description of carbon monoxide, the highest energy electrons, let's see, okay. So I don't think I have carbon monoxide. Okay. Okay, so we need to know the molecular orbital structure in order to answer this question. And I don't think that's given. No, it's not given back here. But, and I think I mentioned this before, carbon monoxide is composed of carbon, which would bond it to itself, would yield sp mixing. Oxygen would not bond it to itself and get no sp mixing. But we showed in one of our slides in the discussion that the carbon influence dominates. So the sp mixing would be evident here in this molecule, right? So what does that mean for, well, if that's the case, then we would use the dicarbon model and just use the order from the document, use the order for the shorthand description, which would be for the valence electrons, would be that, and this, and, well, maybe this one. I don't think we're going to need it, though. Right? How many electrons from carbon? 4, correct? 4. How many from oxygen? 6. So they're 10. So we have 2 here, 2 here. We can have 4 there, 4, 5, 6, 7, 8, 9, 10. Okay? So there's your carbon monoxide molecular orbital structure based upon carbon and its sp mixing. All right, now that we know that, we can probably answer the question. The highest energy electrons occupy anti-bonding orbitals. A is false. The highest ones are in bonding orbitals. How about B? 6 molecular orbitals contain electrons. 1, 2, 3, 4. Oh, wait a minute. There's 2 here. 1, 2, 3, 4, 5. So that's false. Right, there are only 5 molecular orbitals. 2 unpaired electrons. No, those are paired. All of these are paired, paired. So C is false. How about D? The bond order is 3. Okay, 2, 4, 8. Minus 2 divided by 2 is 3. D is true. Bond order of 3. All the above are false. No, we found a true one right there. And in order to answer that question, you have to know this structure. And the key, instead of memorizing it, the key is recognize that the bond order, not the bond order, the sequence of molecular orbitals is based upon sp mixing relative to this carbon. Then you can just go to your chart and write it out. Okay, let's see. How about 41? While we're on this topic. Let's read the question first. Which of the following statements about the CO3 2- ion is false? The carbonate ion, CO3 2-. The orbitals are Sp2 hybridized. Ion is expected to be diamag. Okay, so we're putting valence bond theory and molecular orbital theory together in these selections. So you got to approach both of them. To answer the first one, which is false. So maybe all of them are true. Right. Well, we've got the answer there, so we know that's not the case. But if we don't have the answer, then we got to look at each one. The orbitals on the carbon atom are Sp2 hybridized. Let's see. So you got 4 electrons here. You got 3 times 6 is 18 plus 2. So that's 24 electrons. Right? You have a carbon, 2, 3, oxygen, oxygen, oxygen. That's 6 is 18. That's 6 times 3 is 18, right? They're all used up, all right? So we have a 2- charge on this one. Carbon doesn't have an octet yet. So we have 3 possibilities. We could do this one, we could do that one, or we could do that one. So with a valence bond theory, we have to resonate among 3 different structures, right? But we can still say, if this is a double bond here, then we have 1, 2, 3, right? 3 groups, trigonal planar, Sp2 hybridized. Statement A is true. All right, let's see. Do we have any others that the CO bonds are different lengths? No, they are not different lengths. The problem with the valence bond theory is that they're all the same length, but we can't say that with that model. We have to resonate them. With the molecular orbital theory, oh yeah, they're all the same length, and we can prove it by bond order. The ion has a total of 24 electrons. Yep, that's true. So D is true, and we know that A is true. We just don't know about, well, we know that C is false, right? So E can't be true. So we found our answer. But I wonder, is the ion expected to be diamagnetic? Well, the problem here is that we didn't discuss molecules with 4 atoms in them on the molecular orbital scale. So I would say if you found that this one is false, right, and E can't be right, then C has to be the only answer. The ion is expected to be diamagnetic, probably, right? If we found a false one, then B should be, it's probably true. But we don't have the expertise to actually draw the molecular orbital structure of carbonate ion. So we have to go with test-taking technique, and C is the best answer. All right, let's see. How about let's see. That's the problem with flipping around so much, and I'm running out of time. Okay, let's do 42. We've talked about the benzene molecule before, so this one should go fairly quickly. Right? How many electrons are involved in pi bonding in the benzene molecule? Like that. So there's a pi, there's a pi, there's a pi. Each bond, whether it's sigma or pi, needs 2 electrons. So we got 3 pi bonds, that means 6 electrons. And that's based upon the valence bond theory. Right? The molecular orbital theory would be slightly different. Hopefully it would agree. In fact, the molecular orbital theory should, if it's an advancement over the valence bond theory, should incorporate everything that the valence bond theory was able to say about a molecule. And it should be able to say it also plus some. In other words, fix problems from the valence bond theory and incorporate all of its strengths together. So the answer to this one is D. Yeah, 6 electrons in pi bonding orbitals. In fact, sometimes you'll see the benzene molecule written like this. Like that. Actually, that's accurate, because it doesn't claim that any one of those bonds is double. It says this bonding structure is delocalized. All right, let's see, what shall we do next? Okay, just a second. Yeah, we could do this one. I'd have to backtrack though. Go back to 31. There. Which of the following has the largest bond order? So we've got dinitrogen. Go down to E. Yeah, okay. And then we have this sequence here and here. And then we go positive into plus into 2 plus. Okay, so we're going to start from our neutral position. And to do this one, all you have to do is go to the back of the document and find your dinitrogen. Back here somewhere. Here we go. And of course, it's sp mixing. So you'll have sigma 2s, you'll have sigma 2s star, and you'll have pi 2p, and you'll have sigma 2p. And then you'll have, we're going to need an extra orbital, I think. So the next one will be sigma star 2p. Okay, because these are flipped. All right. So nitrogen has 5 each, so that's 10. So we have 2, 4, 4 more is 8, 9, 10. Right. So we don't need that one for the neutral atom. If we add an electron, where does it go? Right here. If we add 2, we have 2 there. If we subtract from here, then we get this one with only 1. And then if we subtract that one, now we're stuck with that situation right there. Okay? So now let's do the bond orders. Well, we know the bond order for this one is 3. We've already calculated it. So what happens if you add an electron to an anti-bonding orbital? You decrease it by half because you're adding it to an anti-bonding orbital and dividing by 2. So this one's going to be 2.5. This one's only going to be 2 because you added 2 electrons. What about this one? Well, if you subtract an electron from a bonding orbital, you do the same thing as adding to an antibonding. So this one's going to be 2.5. And this one's going to be 2. So this is the largest bond order, is the dinitrogen neutral atom. Any of these ions will be lesser in bond order. All right, okay, so that was 31. Now we can maybe get back on track. I thought that was important enough to backtrack a little bit. Okay, so how about, let's see, I know which one I'm looking for now. You know, maybe I can find it, maybe I can't. Ah, here we go. Number 60. So let me speed things up here. Let's do that, and then we'll scroll down to, oops, here we go, 60. All right. So we've got a table here that we're going to fill out. Okay. We've got molecule A, B, and C. We've got A, B, and C. And then we've got various things that we want to describe about these. All right. First is electronic gem. Then we have what type of hybridization is it? And then bond angles. And then example. Okay. There we go. All right. And then the text of the problem tells us something about each one of the molecules. All right. We're given this one, Sp3 here, Sp3. Now I'm going to use a different color for the rest because that's given. All right, these three molecules. Molecule A has hybridization Sp3, that's given. Molecule B has 2 more effective pairs, electron pairs around the central atom. Two more pairs. Right? So that means you need 2 more orbitals. So how do you get 2 more orbitals when you've used up all these? Well, you just add a couple of Ds, right? Molecule C consists of 1 sigma bond and 2 pi bonds. Right? It's not related to A or B in those terms. If it has 1 sigma bond and 2 pi's, let's see. Three molecules. I was looking for more details. I'm sorry. 2 more effective pairs, electron pairs around the central atom. Right. If it has 1 sigma bond and 2 pi's, how could that be? How can you get a sigma bond and 2 pi's? Well, one way is you can have a triple bond. Right? You can have like that. What if you had, excuse me. No, that wouldn't be it, because that'd be 2 sigmas, right? The only way you can get, well, you could do this, but that'd be 2 sigmas and 2 pi's. The only way to get 1 sigma and 2 pi's is a triple bond. I just had to convince myself of that fact. So that being the case, the hybridization has to be Sp. Right? Now, how about the electronic geometry? This is tetrahedral. This is 2, 3, 4, 5, 6. Octahedral. And this is linear. Okay? How about the bond angles? Tetrahedral, your starting point is 109.5 degrees. You just have to memorize that one. How about octahedral? You have to think of octahedral in your brain. Around the central square, they're all 90 degrees. But from one apex to the other is 180 degrees. And from one apex to anybody on the square is 90 degrees. So there are really only 2 bond angles there, 90 and 180. Linear is easy. That's it. So how about examples? What molecules have triple bonds? Well, we just talked about one, right? Dinitrogen, carbon monoxide also. Those are good examples. How about an octahedral molecule? Well, anything with 6 around the, and it could be, for this electronic structure, you could have some lone pairs also. But a good example would be sulfur hexafluoride, right? You got six groups around that sulfur. How about this one? Well, this one's easy. Methane or carbon tetrachloride. Okay, examples. That was 60. Now let's see if this red will erase. That's doing pretty good, actually. There's a little ghosting there. Not too bad. Okay, see when officially it's over in 5 minutes. I know I'm not going to finish, so I might as well just take my time with the rest of them. Let's see. How about let's see. Yeah, next page. This one. Draw a molecular orbital diagram for O2 and N2. And then use the molecular orbital theory to explain why removal of one electron in oxygen strengthens the bond, while removal of one electron in nitrogen weakens the bond. All right? So to draw this structure, you don't have to memorize that. Just look at the useful information. It's right there. Right there in that chart. Where is it? I know it's in here. Right, there it is right there. Right. Just take that chart, and copy it down. Fill in the electrons. And then answer the question. Removal of one electron in oxygen strengthens the bond, while removal from nitrogen weakens the bond. It's easy. Removal of an electron from oxygen over here on the right, you're removing an electron from an anti-bonding orbital, which always strengthens the bond. Whereas with nitrogen, you would be removing an electron from a bonding orbital, which weakens right? And just put it in words. Okay. Let's see. We might be able to finish on time. How about let me back up a little bit here. All right. Well, I'll get there eventually. I wasn't as well prepared today as I usually am. Yeah, how about 32? Maybe even 31. No, we did 31 already. Yeah, we've done 31. I should have checked that one off. Check that one off too. 32. All right, so let's speed things up here and go back to 32. Next page. There. 32. Oops. I want to use red. Okay. Order the following from the shortest to the longest bond. Right. So what do we need to know? Well, it would help. It would be definitive if we could determine the bond order, right? If we could determine the bond order of each one of these, then we could order them by the shortest to the longest bond, because the shortest bond would be the strongest, the highest bond order. So let's say we have C2, B2, H2, and N2. Okay. Well, I'm going to give you a shortcut. Well, we already know N2. We've done that one before, dozens of times. That bond order is 3. The carbon-carbon, well, hydrogen-hydrogen, of course, is 1. It's only got 1 electron. No, actually, it's 1/2. Let's see. No, 2 electrons. It's 1. Yeah. Because they both go into the first bonding orbital. Divided by 2 is 1. Okay. How about boron? Well, we might have to look up boron. Right. So you go to your table in the back, and we find boron is Sp2s with 2 electrons, Sp2s star with 2 electrons, and pi 2p with 2 electrons. So that's 2 plus 2 is 4 minus 2 is, that's equal to 1, isn't it? Yeah, that's equal to 1. And oxygen, carbon. Yeah, carbon. Carbon will be the same order here, but carbon has, instead of 3 and 3, it has 8. So carbon would be like this: 2 here, 2 here, and 4 there. So we would have 4 plus 2 is 6 minus 2 is 4, and bond order would be 2. 2, 1, 1, 3. All right, so how do we put those in order of bond strength? Well, the shortest bonds Am I looking at the right one? 32. Here's some people leaving already. That's okay. 32. Here we go. Shortest to longest bond. Okay. Shortest bond would be you would expect the shortest bond to be the strongest, but we're dealing with different size atoms. So this one is actually sigma 1s 2. This is going to be the shortest bond. It may not be the strongest, but it will be the shortest, simply because we're smaller atoms are closer together. So this is the shortest, right? H2. Okay, let's bracket in the other end. Boron is a bigger atom, but it's only got a single bond. So it's going to be out here. It's going to be the longest. Then we need to put the order in here. So carbon and nitrogen are in the same period. So the bond order matters here. So this is going to be the next shortest, and this will be the next shortest, right? So that one's a shorter bond, and this one is a shorter bond, and that one's a shorter. So it would be H2N2, C2, and B2. A. Well, let's see. Do I have anything to gain by doing any more? We've done all the really serious ones. So if you're limited on time, stick to this version 2 review and just be sure you understand all of those. And I guess I better call it a day.